So last time we did this example, or finding our local extremas, right? We found out that local extremas happen when the function is changing from increasing to decreasing, right? Or in other words, when the first derivative goes from positive to negative, right? That gives us a max. Or if it's going from negative to positive, which gives us a min, right? Either way, those are the extremas, right? That's all it is. Get the first derivative, set it equal to 0, you get critical points. Now, are those critical points max or mins? You have to find out the increasing, decreasing around it. That's all there is to it for that, right? Now, what I wanted to show you was the last problem we did. I just want to show you a graph of it and take a look at how it looks like. So the critical points not only happen when the derivative is equal to 0, but it's also when the derivative is undefined. Do you see the two undefined derivative points on here? Right? That's right here at x equals to negative 2. That right there is an undefined derivative, and at x equals to 2, which is right here, right? Which is this point right here. We also found another critical point at x equals 0, right? And that happens to be right here. But can you guys see what the derivative entails for the graph? Like right here, for this interval, we found out that the derivative was what sign? It's negative, which means the function is decreasing. Look at the function, right? Is the function going down from left to right? Yeah, yeah. What happened here when the derivative was positive? It's increasing. Does it look like it's going up? Yeah. Right? And it's not even Tuesday. Now, over here, negative, still what? Decreasing. And over here, positive, increasing. And that's all the first derivative does. It just tells you when is your function increasing, when is your function decreasing. And you can get specific intervals if you know the critical points, right? Because the critical points is the only time it could have possibly changed from positive to negative, right? So that's all well and good for, first derivative. That's awesome, yeah? There's also stuff that you can find out from the second derivative, and that's what I want to start off with today, right? Today's lesson is going to be the second derivative test. Yeah, there's no third derivative test though, but there's a second derivative test. So let's write this out here. So let's write this out. The second, and apologize for my sloppy writing, derivative test. Can you read it?
Kind of, yeah.
Okay, so the second derivative test talks about concavity. Have you ever heard of concavity before? Concavity. Not con, but con. Not KH, not con, but con. So, let me show you. A function.
A con artist, huh?
Yeah, actually, that's the same type of con. Is concave up when the second derivative is positive. Right? So, what does concave look like? Concave up looks like this. Ta-da. Convex, I'm so nice that you brought that up. So back in my day, we used to learn the term. We learned concave and convex, right? And they use that for lenses, right? Concave would be caved in, convex would be popping out. That's all well and good for like lenses, but when we're dealing with these graphs, we don't actually use convex anymore because it's hard to say direction, right? So instead of saying concave is for everything facing up and convex for everything facing down, we just say concave up and concave down, just to make it easier. But convex is the term that I learned, and I was like, why did I learn this term?
Look at the evolution of that.
But yeah, you still will use convex and concave, especially if you go into physics. It is important to know the difference of those two. But for just graphing things, we can see the orientation of which way is it's concavity. I don't know why that was so hard to say. But yes, so check this out. Not only do you know when something's concave up, you can also know when something's concave down. A function, you can just put quotes around this if you want, or ditto marks if you want, it's the same thing. A function is concave down when the second derivative is negative. So how does that look? It just looks like this, right? Just going down, okay? Now, if you combine this with the stuff we learned for the first derivative test, you can get a general idea of what the shape of the curve should be. So what does that mean? You can actually have graphs that are both concave up and increasing. That looks like this. When a graph is concave up and increasing, that's when your graph is just climbing a lot faster than anything else, right? So here's an example of something that is concave up, and it's also increasing. You could also have something that's concave up and decreasing, where it's going like this. Concave up, and it's decreasing. That's just terrible. I'm going to rewrite that again. Decreasing.
Wait, oh, but it's going up.
It's still concave up, but it's going down.
But then you could consider the other one.
No, because we read our graphs from left to right because we live in America.
Okay.
I'm just
So
kidding.
let's just live in the-
I'm just kidding. So that's the idea, though. We are going from left to right, and that's why the top one is considered increasing, right? Because we're always going from left to right. Okay? So that's why it's concave up and increasing for the top one, concave down, decreasing. And they're like, oh, they look the same and they're mirrored, and that's exactly it. Now, for concave down, right, it'll look something like this. If you're looking for concave down and increasing, it's like this, where it's going up, but it's going up slowly at this point. This is considered concave down, but it is increasing. And then you have something that is concave down and decreasing. Right here, this is concave down and decreasing.
My motor skills are not good. I can't write.
Don't worry, me neither. So we got examples of when they're concave up, and we have examples of when they're concave down, right? So, some of you might remember, there was like a big controversy, I think it was like last December, where they were like, this is the highest COVID cases we've ever had in the past, but yet they're reopening things, right? And they're like, why are they reopening things now when the COVID cases are so high, but before, when they were lower, they were closing things, right? Now, there's a reason for this. That's because of concavity. Now, take a look at this. If you have something that's kind of low, like down here, right, but it's still increasing, but increasing with a concave up, look at how different that is for something that's kind of low, but increasing with a concave down. Do you see the speed at which it's increasing at? You know how we talked about position, velocity, and acceleration? The second derivative is acceleration, yes? Right. If you have a bigger acceleration, then your speed is going to increase faster as time progresses. So when you have something that is concave up and increasing, that's where things get dangerous. So even though we had lower COVID cases, but we saw the trend being concave up, that's where people started to freak out. That's what happened with this Omicron variant, right? Omicron variant at the very beginning had a very steep climb, which means that concavity was very, very much concave up, right? Now though, what's happened recently is that it's starting to slow down. It's still kind of increasing, but it's now concave which way? Down. And you can actually kind of see that. I'm hoping my internet's working. Hey, look, you guys look great. So let's say I was looking at COVID cases. Check this out. Look at this graph. So this is in the last 3 months, but if you look at it from all times, right, it looks kind of scary. Right, it looks kind of scary because it's like so high up there, right? But the high part's not the scary part. Again, the scary part is the rate, right? Because if it kept that rate, it would have gotten even higher. But that's the part you need to focus on is right here. you see how right here, if you look at it closely, it's concave up. That's the fear, right? Because if it stayed at concave up, it would have kept on spiking up higher and higher. But as soon as it changes to concave down, it's still increasing, but it's increasing slower. Does that make sense?
Yeah.
Yeah? Yeah?
Wait, because it's concave down, right? So it's still increasing.
Yeah, here. Does that kind of make sense, or? Yeah. So this is like basic stuff that happens a lot with like diseases. It's always going to at some point teeter and start concaving down, right? We just want that to happen sooner most of the times. But what's interesting about looking at concavity is, did any of you play baseball or softball? Have you ever heard of a rising fastball?
Yeah, right one. Yeah.
Yeah.
It's literally it's only for softball.
So it looks like, well, yeah, it's more prevalent in softball, but in baseball, it's not actually rising. But when you're standing there, you swear it looks like it's rising. So the idea is, when you see a pitch, a person's pitching from up here and the ball's coming down, right? So when you're standing there at bat, you'll watch a baseball come towards you and you see it trending down. But if the second derivative of that ball is positive, it goes down slower. And that little bit of slow movement actually makes it look like it's climbing. And that's the idea behind the second derivative here. It's just like, having that particular value can adjust how it changes how it looks to you. And that's kind of like, I don't know, I think it's kind of neat. It's like you can actually see it happen, but it all depends on whether or not can you tell if it's, concave up or concave down. Anyways, let's do a problem. And let me show you how to find out if a function is concave up or concave down. Okay? So let's go ahead and go over here. Let's do an example problem right here. Well, that's not a pen. So let's go here, zoom in a little bit here. Yeah, example problem. That is, I don't like how that looks. Let me try it again. Still looks just as bad, but that's okay. It's because let me adjust that there. Here we go. So for this problem, let's say I was asked to find the concavity. Concavity is a fancy word for concave up, concave down, right? Of the following. Of the following. So let's say I had this function right here. Y is equal to 3 plus sine of x. I'll give you guys a second to copy that.
The word concavity actually makes sense. It's just like pronounced weirdly, but phonetically it makes sense. Like the concavity of something, if that makes sense. Like when you hear concavity, you think of con and cavity, like like a hole or something. So like the concavity of something. Like I don't know how to explain it.
I just like that for this problem, all I have to do is write one word as opposed to the other problems where I have to write down, tell me where is it increasing / decreasing. They don't have a word that talks about that, Actually, I think there is one. I just don't know it. But concavity tells me I got to find both concave up and concave down. All right, so how do we do this problem? It's the exact same thing as finding out when a problem is increasing or decreasing, right? Because increasing or decreasing happens when the first derivative is positive or when the first derivative is negative, right? Concavity happens when the second derivative is positive, concave up, and when the second derivative is negative, concave down. So we, as a class, need to figure out when is the second derivative positive and when is it negative. We'll do that by finding out when is the second derivative equal to 0 and then splitting it up into regions, right? Because that's the only time it will change from positive to negative if it changes at all, right? So let's find out when the second derivative is equal to 0, right? So first derivative, what's the first derivative of this problem? Cosine of x, very good, right? Because derivative of 3 is 0, derivative of sine is cosine. And if I was looking for increasing, decreasing, I would start here, right? This would tell me when is it increasing and when is it decreasing, right? That's what the first derivative is for. Second derivative, though, let's do that real quick. Second derivative is, what's the derivative of cosine? Negative sine of x. This is going to tell us when it's concave up and when it's concave down. Oh, I forgot. This problem needs to be on an interval, or else we'll be doing this for infinity. Let's do this on the interval from 0 to 2 pi. That's the standard, for trig functions, right? From 0 to 2 pi. I'm sorry, Stephen, were you about to say something? If the second derivative is negative, it's concave down. but we don't know if it's negative yet. We just found the function. We have to plug in values to figure out where it's negative, right? Because right now, yes, there's a negative sign there, but if you had like negative, negative, it would become a positive. So we just got to figure out where the values are for positive. So let us find when the second derivative is equal to 0, first of all. When is negative sine of x equal to 0? What? Yeah, when x is, good, good, we can do it that way, when x is. Do you remember when does sine equal to 0? No. X is 0 is one of them. There's two more. 2 pi is another. There's one more. No, let's do it between 0 and 2 pi, just to keep our lives easy. We got 0.
Not pi over,
It's not 1.
It's, I don't remember, yeah.
90 degrees is sine is equal to 1. Pi over 2 is also when sine is equal to 1. That's equal to negative 1. That's root 2 over 2. It's just pi.
I was going to say that next.
Gee, come on, guys. Remember your unit circle. Sine is
I'm sleepy today.
sine is equal to 0 here and here, right? And that's at 0 comma 2 pi, and that's over here at pi.
Sorry, I'm a spring break myself.
All right. Here's the thing, though. I don't really care about the 0 or the 2 pi. Why? They're not within the interval. If we had no. We don't discriminate against numbers, right? We go by rules, and the rules is that 0 is on the endpoint, but it's not including that endpoint, right? If they had drawn it with a bracket, then I would include it. But since they drew it without the bracket, I don't include those endpoints. So the only, I'm going to use my quote fingers here, critical points that we have is x is equal to what? X is equal to pi. That's the location where the second derivative might possibly change signs from positive to negative. Okay? So let's do that real quick. We got our two regions here. We got this region, which goes from blank to pi, and then this region is going to go from pi to blank. Now, before we would put negative infinity to that number, and then we would go from that number to infinity. Why am I leaving that blank and not putting infinity or negative infinity? Yeah, it's on its own interval right now. So instead of going from negative infinity to pi, what's it going to go from and to? 0 to pi, and then pi to 2 pi. That's the only reason for that is, again, you got to pay attention to this part right here, right? They tell us that the beginning interval is from 0 to 2 pi. Does that make sense? Whereas the other problems we did, they didn't tell us an interval, so we just went from infinity and beyond, right? Can't wait for that movie.
Really?
Yeah, looks interesting. The Buzz Lightyear movie.
You really think it is?
I think it's already done.
It's going to be the movie that inspired the toy in that world.
Oh, that's how it's about? I thought, okay.
Yeah.
I don't know. I just feel like
Buzz Lightyear Star
they're
Command.
digging too much into like
Oh,
past childhood.
but you see, I was a fan of the cartoon show of Buzz Lightyear.
I guess it's pretty
Do you remember the cartoon? You don't remember the cartoon of Buzz Lightyear? Oh, that was from yeah, it is a while ago, but it was a really good cartoon. Buzz Lightyear and Space Command, I think it was. Okay, look, we're just gonna waste time and take a look at this real quick. Buzz Lightyear.
See that in the recording as well?
Yeah, they are, huh? Buzz Lightyear Star Command. You never seen this cartoon?
No.
Hold up. No, not that one, not that one. That one. You've never seen this cartoon?
Oh yeah.
Not we, we're not.
Look at it. Look how great it is.
Disney December? What?
Ignore the Disney December. Just look at the cartoon.
What's Disney December?
But you never saw this?
My brother used to watch it.
Ah. Oh
I
well.
remember when I was like small, my brother used to just watch it.
But you guys know a lot of other old cartoons. Yeah, Looney Tunes is older. All right. So anyways, let's come back.
Kept it.
Let's come back over here. Pick a number that's between 0 and pi that I should plug in for x. You could plug in 1, but calculating 1 is going to be a little bit harder. You might need a calculator for it. Pi is not there, but maybe, why not pi over 2? Square root of 2 over 2 is an output value. I want you to give me the input value. So you could do pi over 4, and that will give you square root of 2 over 2. But I'm going to go with pi over 2 because that's halfway in the middle, and that's easy to calculate the sine of. Right? You should know what sine of pi over 2 is. But if you don't, that's OK. We'll calculate it right now. So the second derivative of negative sine of pi over 2. What is sine of pi over 2 equal to? 0. No, 1. Sine of pi over 2 is equal to 1. I have a negative sign in front of that sign, right? So what's negative 1? That's just going to come out as a negative second derivative. So my second derivative is negative on this interval, which means that my graph of this is going to be concave down. That's it. I know that my function is going to be concave down there. I do the same thing for this interval, which is x is equal to, give me a number that's between pi and 2 pi. 3 pi over 2. You could do that. You could also do 7 pi over 4. You can also do 5 pi over 6. But you know, the easy one to calculate is going to be 3 pi over 2 because hopefully you have that in your mind. The sine value of that is going to be equal to what? Sine of negative sine of 3 pi over 2. What's sine of 3 pi over 2? Negative 1. Negative 1. If you don't know these yet, you can plug them into a calculator. You can see it that way. You can also plug in other values that are between there and still get, because remember, we don't care what the number value is. We don't care about the decimal. We just care about the sign. So I'm going to end up with negative 1, which tells me this sign is going to be a positive sign, which means this is a concave what? Up. Concave up. Concave up. We don't know if it's increasing or decreasing. We just know that the shape of it is like this, right? And we know the shape of the other thing is like that, right? Concave up and concave down. I'll give you a second to copy that. If you already did, that's good. I'm going to go ahead and then get the graph of it over here and put this over here. So remember, what's the original function look like? What's the original function we're dealing with here? It's 3 plus sine, right? 3 plus sine of x. That's the original function we were dealing with, yeah? If I were to graph this on Desmos and look at it from 0 to 2 pi, what's the sine graph look like? It's just that, yeah, the little like wave, right? And here it is. What's up? So, you see the concave? Yeah, I'm glad. So check this out. Let me line up this right here with our region that we just found out, right? We found out that when x equals to pi, we have this little point right here where the second derivative changes sign from positive to negative, right? So check this out. The second derivative was negative, which means that the graph should be what? Concave. Look at the graph. From 0 to pi. Does it look like it's concave down? Yeah, I'm not looking at the increasing, decreasing, right? I'm looking at the concavity, right? So it's concave down. Look at it when it's from pi to 2 pi. It has a positive sign, which means it's going to be what? Concave up. Can you see it? And there you go. So we have concave down and concave up. And this x equals to pi right here, it's not a critical point when it changes sign in the second derivative. It has its own special name. Its special name that we give it is called a point of inflection. Point of inflection. A point of inflection is the second derivative version of a critical point. It's where the sign changes from positive to negative or negative to positive. The only difference is there's no max or min. It's just a critical point. You can kind of see that right here, right? So again, this point right here where x is equal to pi, we call that the point of inflection. Point of inflection. Now, if I had did the first derivative test, can you guys just take a guess of where your critical points would be on this problem? Where's your first critical point? Where do you think that would be at? At the top? Anyone have a guess, by the way, to what that x value is? This is going from 0 to pi to 2 pi. Anyone have a guess for this one? Pi over 2. And if you were to actually take the first derivative instead equal to 0, it's equal to 0 at pi over 2. And the other one would be over here. Anyone have a guess for this one? X is equal to? 3 pi over 2. Very good. Check this out. If you cut that down and get those regions, like we did for the second derivative, you'd have what we did last week for the first derivatives. Meaning the first derivative is going to be positive from here to here because it's clearly what? Increasing. So from 0 to pi over 2 would be an increasing. From pi over 2 to negative 3 pi, I'm sorry, to 3 pi over 2 would be a negative derivative, which means that it is decreasing there to there. And then from 3 pi over 2 to 2 pi, I would say that it is a positive derivative, meaning it is increasing. Okay? So think of this chapter, right, as just us applying derivatives now to tell us things about functions, right? We did all the practice on calculating derivatives, right? We did chain rules, product rule, quotient rule, techniques, and all that stuff for derivatives. Now all we're doing is applying them to graphs and seeing when is a function increasing, when is a function decreasing, when is a function concave up, and when is a function concave down. These are the applications to it, and they're pretty much the same. Take the derivative, set it equal to 0, get regions, and test if they're positive or negative. And that's what it is for this as well. So I'm going to pause this here, and we're going to continue this tomorrow. And I'll give us some more practice problems so we can see what to do with this information, okay? But that's it for today.